when I have the positive half of my sine wave on the primary side, at the secondary side, what does the voltage look like? It looks just like this, except it's going to be a little bit smaller, right? Based on the turns ratio. So it will be still a sine wave, only smaller in size. So plus and minus. Let's look at the positive half, case 1. For the positive half, when I have the positive half of my sine wave, the polarity I show is plus at the top and minus at the bottom. That's the positive of a, anytime I have a circuit like this, right? This side is plus minus, so this is my plus and this is the minus. So that's what I'm showing here. That the positive half of my sine wave gives a polarity of plus at the top, minus at the bottom. So now I look at how the current is going to flow from the plus to the minus through the diodes, depending on which diode is forward biased, which means that it acts like a closed switch, and which diode acts like reverse bias, which means that it acts like an open switch. So, with a plus at this diode here, okay, plus at diode 1, we'll call this D1, is D1 forward biased or reverse biased?
Forward.
Plus on the anode, it's forward biased. Okay, let's look at D2.
Reverse.
Minus at the anode, reverse bias. Let's look at D3. Minus at the cathode, forward bias. D4. Plus at the, sorry, one more time. Minus at the cathode, this is forward, yes. Plus at the cathode, reverse bias. Okay, so that's what happens with the polarity of my positive half sine wave, is that diodes D1 and D3 are forward biased, and D2 and D4 are reverse biased. So think of these two as closed switches, and D2 and D4 as open switches. What that means is that I go to page 11 and look at the circuit at the bottom of page 11. That's what I'm showing here. That these two diodes are forward biased and the other two are reverse biased. So look at the way the current's going to flow. From the plus, just like a mouse maze, it's going to go from the plus through D1 into the load, through D3, out to the minus. Current has to flow from the plus to the minus, and it found a way to flow. It was flowing through D1, through the load, through D3, and back. And when it was flowing through the load, where it comes in is plus, where it comes out is minus. So that's the polarity of the voltage at the load, and I show that here like this. So this is the voltage at RL. And that's what's shown in the graph at the bottom of page 11. Okay? Now let's look at the negative half. When I have the negative half of my sine wave on the primary side, it gets smaller in size on the secondary side, and with a minus voltage, the polarity here changes to minus and plus. Why? Because minus voltage it's like having a DC voltage with minus at the top and plus at the bottom, which means that my references are now reversed, minus at the top, plus at the bottom. Make sense? So that's the AC voltage minus at the top, plus at the bottom. Everything changes now. What was forward now becomes reverse. What was reverse becomes forward. Let's see. Plus here on the anode side, so this guy becomes, D2 becomes forward. You see? Reverse becomes forward. On the other side, also with the plus here, D2 was forward, but D3, which has the cathode now positive, so the forward becomes reverse. With the minus on the anode side of D1, that's no good, reverse. Minus on the cathode side of D4, reverse becomes forward. So what was forward becomes reverse, what was reverse becomes forward with the negative half cycle. And now let's look at the current flow from the plus to the minus. So I start out here, forward here, so current goes up, through the load, forward, and back. It cannot flow through these open switches, the reverse bias diodes. And this is shown on page 12. So if you look at page 12, it shows with the dotted line arrows the way the current is going to flow through the two diodes that are forward biased. Okay? And what's amazing is for both cases, the current through the load is going to flow in the same direction. And so where it comes in is plus, where it comes in is minus, and that results in a second voltage that looks the same as the first voltage at the load. Okay? So over the two positive and the negative half cycles, this is what the voltage at the load will look like. And so on a scope, when I connect this circuit, this is what I will see. And this is called a full wave graph. Okay? So the result is the same as the two diode rectifier circuit. In a two diode rectifier circuit, we get the same result. Because the result is the same, whether you have two diodes or four diodes, what's the advantage of the four diode rectifier circuit? The main advantage is that with the two diodes, we needed a center tap transformer. And the construction and the cost of a center tap transformer is more than putting a diode. Diode is cheap. Building a transformer and going during the fabrication of it and hooking up that third lead, all that is process that is expensive. Okay? And if you look at the costs of these transformers, the one that we're using in the lab, it's something like $15 or $20 for a transformer. And the fact that it's center tap makes it even more expensive. Whereas a diode is like a 5 or 10 cent item. So adding two more diodes is much cheaper than using a center tap transformer. Make sense?